Hey everyone, and welcome back to another electrical engineering video. So in this tutorial today, we're going to cover some fundamental concepts in circuit analysis. So we'll be covering branches, nodes, loops, and as well as Kirchhoff's law, which we'll be diving deeper into the video. So these are just important basic concepts that you'll need to know to help you have a solid foundation in circuit analysis. So without further ado, let's get right into it. So here's a quick rundown of what we'll be talking about. So let's start off with branches. So first of all, what are branches? Well, branches are simply, you can think of them as like your typical resistors or capacitors or inductors. They're basically just the circuit elements in a circuit. So let's start off by drawing a voltage source. So I'm just going to draw the circle with a plus and minus for the positive and minus terminal. And then let's say we have a wire sticking out of it like that, and then we connect it with another resistor. That is a branch right there. So a branch is essentially a single element like a resistor, voltage source, or current source connecting two nodes, meaning it has two terminals. So that's the key word there, two terminals. So as you can see, this resistor has a terminal here and then a terminal here. So that's what makes it a branch. And then loops, on the other hand, is basically a connection point between two or more circuit elements meet up together. So this would be a node right here because it's connecting the voltage source and the resistor together. So that's one node. And then if we were to add another resistor, this is also the same node, so it wouldn't really make sense for me to draw a single dot because a node is basically a collection of electrically connected points that all share the same voltage potential. So what you see here, this entire wire right here, that's one node. So if you were to take out a voltmeter or something like that, if you were to take out a voltmeter and measure the voltage across any point on this wire, it's going to read the same potential. So if you were to read the potential here or here or here, it doesn't matter where it is, as long as it's within that same existing node, then it's going to read the same electric potential. So let's label this as node 1, so I'll just write N1. And now, since we drew these resistors in this particular way, we have just created another node here. So this is another node that we just created. So we can just keep adding on more resistors or any circuit elements for this matter, but for simplicity, we'll just use resistors. So let's say we have this resistor here and then another resistor like this. And now if we connect all this back to the voltage source, this entire area right here is one node. They're all connected to, they all have the same electric potential. So once again, if we take the voltmeter and measure any point along this line, this green line right here, it's going to read the same potential. However, as soon as I add another resistor like this creates one more node for us, which connects us all the way back to the voltage source. So while this may not be the best way of looking at it, you can kind of view node as being like the space between these circuit elements. And now lastly, let's go over loops. So a loop is basically just a closed path in a circuit. So let's say you start at one node and then travel through the connected elements, returning to the original node without tracing any component. Then basically you've just formed a loop. So here's what I mean. So let's draw the path of the loop. Let's say I started this point here. So if I started that point and I go clockwise, it doesn't really matter which direction you go, but let's just say we go clockwise. So I go around this closed path right here and then make my way back to the same point without crossing over the same point twice. Then I've successfully completed one loop. This can also be a loop as long as I make it back to this point right here. Or I can start at this point and then take a longer path. So let's say I start at this point and then I go around and around to the end of this terminal on the third resistor and then loop my way back to the initial point. That's also another loop. And there can also be a mini loop like this. That's one loop. And this is also a loop. This is also a loop. So hopefully you guys are beginning to see the pattern on how loops work. It's basically just a closed path in the circuit. So you can pick any point you want, and as long as you return to that same point without crossing over it twice, then that's one loop. But it has to be one complete path. So while we have these four main loops here that we see, there's also one more giant loop that we can also trace. So if we start at the voltage source here and then walk our way around like this through the perimeter of the circuit diagram and then make our way back, that's also another loop. And I don't know why I did that, but Anyways, hopefully that made sense. So now let's use this knowledge that we learned here and practice some Kirchhoff's law problems. So Kirchhoff's law has two parts to it. It has a law describing the voltage and also a law describing the current. And we can abbreviate Kirchhoff's voltage law with just simply KVL. So that's Kirchhoff's voltage law, and then Kirchhoff's current law would be KCL. So let's start off with KVL. So what does this law describe to us? Well, it basically states that the algebraic sum of the voltage drops in a circuit is 0. So mathematically we can express it like this. It would be, you would start by drawing your sigma notation, and then the sum of all the voltage drops is 0. And the reason why this is because if you start at a certain point and travel around a loop through various voltage rises and voltage drops, you'll eventually come back to your starting point, which is how a loop works. And since you must end up where you started, the total change in potential must also be 0, since the displacement is 0, if you want to think of it that way. So another way of expressing this formula here would be Vn. So that's the voltage coming in equals the voltage coming out. So it doesn't matter how you assign the positive or negative signs, but one of these will have a positive sign and the other one will have a minus. So when you add them together, they just cancel out to form 0. So let's draw a diagram demonstrating Kirchhoff's voltage law. So here's a quick diagram I just sketched out. I know my drawing skills aren't great, but we'll make it work. So let's label this V1, and let's label this V2. This will be V3. Let's call this V4, and then this will be V5. So if we assign this to be the negative terminal of the battery, and this is the positive terminal, then based on conventional current flows from a high potential to a low potential. So let's pretend that we're going clockwise in this circuit diagram here. So if we're going from a positive to a negative, that's not a voltage drop because it's contradicting conventional current, so it's going to be a voltage rise. So we can give it a positive V1 here, and then as we make our way throughout the circuit, this will be a positive terminal, this will be a negative. So going from positive to negative, that's a voltage drop. So we're going to subtract V2 from V1, and then this will be the positive side, this will be the minus side. So once again, going from positive to negative, that's going to be a voltage drop. So let's subtract V3, and then this will be the same thing. This will be a positive, this will be a minus, going from a positive to a minus. That's going to be another voltage drop. So I'm running out of space here, but that's minus V4. And for the fifth battery, we're going from the positive terminal to the negative terminal. So that's another voltage drop. So that's going to be minus V5, and all this will be equal to 0. So now before we solve for all these variables and assign a different equation, let's briefly go over what voltage drops and voltage lifts are. So let me scoot down so we have some space here. So let's say this is our battery again, and then this is the negative side, this is the positive side, and then current is flowing in this direction. So as you can see, it's going from positive to negative. So that's going to be a voltage lift because it's going from a low potential to a high potential. So this is a voltage lift. And if we take that same battery again, except this time we reverse the polarity, so this is going to be the positive side and this is going to be a minus side, and the current is still flowing in this direction. Now we're traveling from a high potential to a low potential since the current is going from the positive end to the negative end. So this is going to be a voltage drop. And all this should be relatively intuitive because going from a high point to a low point, you can think of it as jumping off of a mountain, which is a pretty extreme example, but when you jump off of a mountain or just any point that is higher than the ground, then you're jumping from that higher point to a lower point, so you're essentially being dropped. You're dropping yourself. So this is a voltage drop. So hopefully that made sense there with the analogy. And now let's take what we have up here, this equation right here, and solve for V1. So as you can see, V1 is the only positive variable while all the other variables are minus. So therefore, it's just going to be V1 is equal to the sum of V2 plus V3 plus V4 plus V5, which describes the behavior of this circuit. So essentially, however you travel in this circuit, if you make one complete loop and end up back to where you started, then the sum of all the voltage drops will just be zero because there has been no change in electric potential. So that's basically it for KVL, and now let's move on to KCL. So for KCL, it states that the sum of all the currents at a node must vanish. So basically what it's saying is the amount of charge entering a node must be equal to the amount of charge leaving a node. So we can express it with this mathematical formula right here. So IN, so I is just current, so this is the current coming in, equals the current coming out, or rather just leaving the node or the junction. And we can also express this a second way. So it's simply just going to be the sum of all the current is equal to 0, because once again, if we assign one of these to have a negative value and the other one to have a positive value, a positive plus a minus will just cancel each other. So let's draw out an example and demonstrate this further. So imagine we have a node right here, and then we have two circuit elements. These don't necessarily have to be batteries, they can be whatever you want, but I'm just going to draw boxes to keep things simple. So let's say we have these two circuit elements right here connected to a node. We're going to have some current flowing in this direction, which we'll just call I1. So based on the direction of the arrow, the current is flowing towards the node, so it's entering. And let's assign a positive value for currents that enter a node and a negative value for current leaving a node. So we have I1 flowing in this direction, and then I2 is flowing in this direction here. And as you can see, it's flowing in the opposite direction of the node, this yellow dot I drew right here. So it's leaving the node. So if we take our formula we had up there, it was the sum of all the current must be equal to 0. So it's going to be the sigma notation I is equal to I1, because it's a positive value, minus I2, and that's going to be equal to 0. And since we know that I1 minus I2 is equal to 0, I1 must be equal to I2. So this is a pretty useful way to help you use algebra to solve for missing variables in a Kirchhoff's voltage law or current law problem. So let's try another example. So let's say we have a node right here, and we have current flowing in all directions. So we'll have one coming in this way, another one this way. So basically, you can think of it as like a four-way. So it's the center point. So we're going to have some current which we'll call I1 flowing in this direction. And then let's say we have another current I2 flowing in that direction. I3 is flowing in this direction. And then I4, we'll just add it for fun. We'll just draw it diagonally like this. Let's say I4 is flowing towards the node in this direction. And lastly, let's do the fifth current, which is leaving the node. So let's start off by identifying all the current entering the node and all the current leaving the node. So I'm going to highlight the ones entering the node with the color green. So I1 is entering the node, I4 is entering the node, and I5 is leaving the node, I3 is leaving the node, and I2 is leaving the node. So the sum of all the green currents is equal to the red current, basically is what this is saying. So I1 plus I4 is equal to I2 plus I3 plus I5. And if you want to, you could also wrap all these in parentheses, and if we were to move all this over to the other side, then this side will be 0, and this will be I1 plus I4 minus I2 minus I3 minus I5 is equal to 0. So this equation right here basically describes the essence of Kirchhoff's current law. So the sum of all the charges in a circuit has to equal 0 if you travel in a closed path, which is called a loop once again. So now let's assign these currents some values and leave out one missing value for you to solve. So if we're given that I1 is 3 amps and I2 is also 3 amps and I4 is 7 amps and I3 is 2 amps, then using this information, how would you solve for I5? Well, as you might guess, this is just simple algebra. You just plug in what you have. So we know I1 is 3, I4 is 7, I2 is 3, and then I3 is 2, and we're solving for I5. So, and all that will be equal to 0. So 3 plus 7 is 10, 10 minus 3 is 7 again. Minus 2 is 5. So we have 5 minus I5 is equal to 0. So it's simply just going to be 5 is equal to I5. So I5 is 5 amps. So congratulations if you figured that out. And now, before we dive any deeper into some more complex Kirchhoff's problems, let's try out another example in this format for Kirchhoff's voltage law. Okay, so here's an example that I put together to help you understand KVL. So pretty much we have this circuit diagram here with a bunch of batteries connected together of different voltages, and I included the polarities for all the batteries, and our job in this problem is to find Vx, which we don't know the voltage of yet. So using Kirchhoff's law, that will help us solve it. So to start off, let's define the direction in which we'll be traveling in the circuit. So we'll be going clockwise. So if we start with the 6-volt battery here, that's going to be a voltage rise because it's going from the negative terminal to the positive terminal. So we have a positive 6 volts here, and then as we make our way around the circuit, we're going to go from the positive to the negative end of the 20-volt battery. So we're going to subtract 20 volts, and as we go through the 10-volt battery, that's going to be another voltage drop of 10 volts. And then Vx, we don't know the value of it, but we do know that it's going to be a voltage drop because this is a positive going towards a negative. So let's subtract Vx. And when we go through the 18-volt resistor, unlike the, not resistor, but battery, I keep saying resistor. But as we go through the 18-volt battery, that's going to be a voltage rise because it's going from the negative to the positive. So let's add 18 volts. And now all we have to do is just add up everything and solve for Vx. So the sum of all these voltage drops is going to be 0 according to Kirchhoff's law. So now we just do mental math again. 6 minus 20 is negative 14. Minus 10 is negative 24. So we currently have negative 24 volts minus Vx plus 18. So to clean up things, this is going to give us negative 6 volts minus Vx is equal to 0. So therefore, negative 6 volts is our voltage value for Vx. And if you might notice, we got a negative voltage value for Vx. So this means that we simply just have to reverse the polarity of Vx. So we initially assumed that it was going from a high potential to a low potential. So if we did assume that, then we would have negative 6 volts for Vx going in the clockwise direction. But if we reverse the polarities, so if we cross these old ones out and replace them with the new ones, so this negative is now going to be a positive, this is going to be a negative, then if we go in the counterclockwise direction, we're going to have positive 6 volts going this. So reversing the polarity simply reverses the voltage, but the absolute value of it still remains the same. We still have 6 volts, except it's now reversed in its direction. Okay, so here's another example of a combination circuit, which we'll be using Kirchhoff's law to solve. So how do you think we should get started from what we already have? Well, let's start by identifying what we do have so far, which are 3 resistors and a 24-volt battery source. And you'll notice that these 2 resistors here, R2 and R3, are in parallel with each other. So you might think that our first step would be to simplify these into their series resistor equivalents and then just add that with a 6 ohm, which you would be partially right. But what we want to do first is identify the current flowing into the node and then identify current leaving the node. So let's call the current that goes in this direction here I1. So I1 is headed towards this node right here, and once it reaches this node, it's going to have 2 paths to choose from. So it could split off and go down the R2 resistor and then make its way back to the 24-volt battery, which is 1 loop, or it can go through this node and then go down the R3 resistor and then make its way back to the 24-volt loop, making a giant loop around the entire circuit. So this means that it's going to split off into 2 other currents, which we can call I2, and then this current here, we can call it I3. So if we use Kirchhoff's current law again, we can set up the equation I1 is equal to I2 plus I3, because I1 is the current entering the node, and then I2 and I3 are the currents leaving the node, so they would get added together to equal I1. And in this case, having too many variables can make it difficult to simplify the algebra. So instead of having I3, we can rewrite I3 as I1 minus I2. And we're going to use that as our I3 instead of actually having a third variable. So let's erase what we have here for I3 and replace it with the current I1 minus I2. So once we find I1 and I2, then we instantly find I3. So now our next step is to come up with two systems of equation that we can use to solve for these missing currents. So if you remember from earlier in the video, we talked about loops and how loops are just a complete path a current takes to make its way back to the original point. So let's define our first loop right here. So this will be loop 1. So it's going to go in this clockwise manner. So I'll just write L1 for loop 1. And then loop 2, we're going to have it go from this point here and then make its way all the way around the entire circuit and then back to the starting point. So we have a giant loop, which is the one in yellow, and then a smaller inner loop, which is L1. So for loop 1, we have a 24-volt battery source, which goes from the negative side to the positive side, so that's a voltage rise. So we have 24 volts. And then as we make our way around this loop here, to go from one end of R1 to the other one, it's going to be a voltage drop, because this is the positive side, this is the negative side. So we can do Ohm's law for this. So it's going to be the current, which is I1 times 6. So actually, let me write it the other way. So it's going to be 6 ohms times I1. And then we're going to go through the 4 ohm resistor, which has the I2 current flowing through it. So it's going to be minus 4 I2. And then we're just going to make our way back to the 24 volt initial point and set all this to 0. So that's one equation we have here. And if you'll notice something, all these are even numbers, so we might as well divide both sides by 2. So this is going to be 12 volts minus 3 I1 minus 2 I2. All that will equal 0. So that's our first equation that we have from loop. So now let's do the same for loop 2. So once again, we're going to start at the 24 volt battery source. So that's going to be a voltage rise, which will be 24 volts. And we're going to go through R1, which is going to be a voltage drop of 6 I1. And we're going to go past the node here, go through R3, and it has the current I1 minus I2 flowing through it. So this is going to be 12 times I1 minus I2, and that is our last circuit element. So we're just going to make our way back to the initial point. So all this will equal 0. Now let's simplify and distribute the 12 to I1 and I2. So this is going to be 24 volts minus 6 I1 minus 12 I1, and then a negative 12 times negative I2 is going to be a positive I2. So this is plus 12 I2, and all that is going to be 0. So we have 24 volts minus 18 I1 plus 12 I2, and all that is going to be equal to 0. So this is our second equation that we have. Now our next step is to eliminate one of the two variables. So we can either choose to eliminate I1 or I2. Actually, I just realized something. To make things easier for us, it would help if we move the 24 volt to the left, to the right side. So our equation 2 is actually going to be negative 18 I1 plus 12 I2 is equal to negative 20. And then we're going to do the same thing for loop 1. So it's going to be negative 3 I1 minus 2 I2 is equal to negative 12. And now we're going to use these equations to plug into our systems of equation. So as we did earlier, so following the same process we did earlier, we're going to try to eliminate one of the two variables, either I1 or I2. So let's scale up the equation for loop 1 by negative 6, so that negative 2 I2 becomes positive 12 I2, which matches what we have here on the left side. So first, let's just start by writing negative 18 I1 plus 12 I2 is equal to negative 24, so that's our loop 2 equation. And then if we scale this up by negative 6, we'll have, now if we scale this up by negative 6 times negative 3 is 18 I1, and then negative 6 times negative 2 is 12, so this is plus 12 I2, and then negative 6 times negative 12 is positive 72. And now let's subtract both of these equations. So negative 18 minus 18 I1, that's going to be negative 36 I1, and then positive 12 I2 minus positive 12 I2, that's just going to cancel out and give us 0, and then negative 24 minus 72 is going to be negative 90. And now if we divide both sides by negative 36, I1 will be 2.6 repeating amps. So this is our current for I1. So if we take one of these equations, it doesn't matter which one, and then plug in what we have for I1, we can solve for I2. So let's use this equation right here. So that's going to be negative 18 times 2.6 repeating plus 12 I2 is equal to negative 24. So negative 18 times 2.6 repeating is negative 48 plus 12 I2 is equal to negative 24. And then if we add both sides by 48, that's going to leave us with 12 I2 is equal to negative 24 plus 48, which is 24. Now divided both sides by 12, we're going to get I2 is equal to 2 amps. So now that we have I1 and I2, we basically have solved the entire puzzle. So let's take our original circuit and then plug in these values and see if they make sense. Okay, so here's our original circuit that I just copied and pasted. So we found that I1 was 2.6 amps repeating, and I2 was 2 amps. So this means that we have 2.66 amps current going in this direction towards the 6 ohm resistor. So we found that I1 was 2.66 amps and I2 is 2 amps. So if we label that here, this will be 2.66 amps of current flowing towards the node, and then once it gets there, it's going to split off into I2 and then I3, which is better known as I1 minus I2. So let's compute I1 minus I2. So 2.66 repeating minus 2 is just going to be 0.6 repeating. So this is how much current we have flowing through the R3 resistor. So we have 0.66 amps flowing through the R3 resistor, and then we're also going to have, sorry if this is getting messy, but we're also going to have 2 amps of current flowing through the 4 ohm resistor. So now that we have everything in place, we can start calculating the electric potential at different points throughout the circuit. So if we start from the very beginning, we have the 24 volt battery source, so that's obviously going to be 24 volts. And then as we go down the wire and then reach this node right here, that's also going to measure 24 volts because it hasn't gone through any resistors or circuit components yet. So there should theoretically be no voltage drop. But as soon as we go through the 6 ohm resistor, that's going to be Ohm's law again. So it's going to be 6 ohms times 2.66 repeating. So the voltage drop for the R1 resistor is going to be 6 ohms times 2.6 amps repeating, which will give us 16 volts, which means the potential at this point is 16 volts lower than the potential at this point. So 24 minus 16 is going to be 8 volts. And then if we go down the 4 ohm resistor, we have 2 amps of current going through the 4 ohm resistor. So 4 times 2 is 8. Therefore, it satisfies the electric potential at this node. So that confirms our work is correct. And now let's do the same for the current flowing through this branch right here. So if we calculate the voltage drop across R3, that's going to be 0.66 amps times 12 ohms, and that's going to give us 8 volts. So once again, that matches what we have here. So therefore, our answer is correct. And the way you can tell our answer is correct or not is pretty simple. So in most circuits that you come across, there will be something called ground. So that's just going to be this point right here. And pretty much at this point, the electric potential is always going to be 0 volts. So this explains why current flows from this node down this path and then towards ground, because it's at a lower potential. And we are done. So let's try out one more example before we wrap it up for the video. Okay, so here's another example you can try out if you want. So pause the video and give it a try, and I'll wait. So first of all, we have a circuit here with 2 voltage sources this time, and I also assigned them their polarities, so that will come into play once we start writing the Kirchhoff's law equations. So first of all, let's start off by defining our currents and the direction in which they flow. So in this direction, we have I1, and once I1 reaches this node right here, it's going to split off into 2 branches. So it's going to split off to 2 different currents. So the current going down this one will be I2. So let's label that here. So this is I2. And then this over here is going to be I3. But as we said earlier, I3 can be rewritten as I1 minus I2. So let's do that instead. So we have fewer variables to deal with. So this is I3, which can be represented by I1 minus I2. So now that we have everything in place, we can start writing our equations. The first thing we'll do is define our loops. So this is going to be loop 1. So this is loop 1, and then this right here is going to be loop 2. So starting with loop 1, we have a 36 volt voltage source. So this is going to be a voltage rise because current is going from the negative terminal to the positive terminal. So we have a positive 36 voltage rise, and then once we go around, we'll come across R1, which if we scroll up has a value of 3 ohms. So if we use Ohm's law, it's going to be the current flowing through R1 times the resistance value of R1. So that's going to be I1 times 3. So this is going to be a voltage drop because it's going from a high to low potential. So 3I1, and then we're going to go through the R2 resistor. So this is going to be minus 8I2 because I2 is the current flowing through resistor 2. And now we can set all this equal to 0. So now let's just move these negative terms to the right side. So that's going to leave us with 36 is equal to 3I1 plus 8I2. So this is going to be our first equation that we'll use in the systems of equation. So let's move on to solving loop 2. So this is equation 1. Okay, so for loop 2, we're going to start at the R2 resistor right here. So this is going to be a voltage rise because it's going from the negative terminal to the positive terminal. So this will be 8I2, and then we're going to go through the 10 volt battery. So this is going from a negative to a positive, so that's going to be a voltage rise. So we can add 10 volts. And then lastly, we're going to go through this 2 ohm resistor here, which has the current I1 minus I2 flowing through it. So that's going to be a minus 2 times I1 minus I2. Well,